This is going to be a quick explanation of the solutions to worksheet 11. So the first question asked you what type of functions is going to make something that looks somewhat like this, a pulse on the left and a pulse on the right and nothing in between. So the right answer are sinusoidal functions, since those will in fact have the correct type of symmetry. And now, depending on exactly what you're trying to match, like I would say this part on mine isn't quite right, the height is a little bit off. The key here is that you're going to get these alternating patterns, and what that gives you is destructive interference right around here. And you can see that clearly here. Half of them are going up, half of them are going down. So right in the center area, you have really nice destructive interference, which means you have a very flat line. But then over here, because these are integer values, right? These are specific harmonics, you actually start to get constructive interference over here, which means you then have pulses. So depending on whether you start with it big and have it decrease, or whether you have it kind of start smaller, this one is actually my biggest one here, you get slightly different shapes, but the key here is to see that you have to have this sort of alternating pattern to actually get this destructive interference in the middle. The second question shows one peak in the middle and then two inverted peaks at the very edge. This has to be made with cosine to have the right symmetry. And now the pattern is actually that to have them all be constructive in the middle, you want to have them all be upwards, but then you actually skip these, right? So this would actually give you kind of the wrong symmetry, that your goal is to have these nice flat regions in between. And the way you would do that is to actually have really nice destructive interference here. So by going every other one, you see that destructive interference point occurs here. And there's kind of this pattern, right? You can kind of imagine tracing this out, and there's roughly a pattern to how it decays. It isn't that I've calculated this out, but by eye this looks okay. And again, there's kind of a pattern here. So the key here is that depending on where you have destructive interference, you expect there to be certain patterns of what components actually contribute, and then the relationship between the remaining components. The next part of the worksheet has you use the discrete to continuous tab, and the first question is, for each of the following changes in the wave packet, meaning down here, what do you need to change in k-space? And k-space is up here. So if you want to increase the space between successive wave packets, so from here to there, what you need to do is decrease the spacing between Fourier components, which is k1. So if I decrease the spacing, we now see that our next wave packet has vanished, and I can zoom out. So as I decrease that spacing further, you now have more and more destructive interference, which again makes our next wave packet even further out. So if we put more space in between them, then in fact our wave packet become close together. So if I go back to some initial setting, if I want to look at the envelope, I can turn this on, and if we want to make the width of the envelope wider, this is where you can start to think about the uncertainty principle. Here it's just a Fourier transform, but if I make the width of the envelope wider, that's the same thing as decreasing my width in k-space. And so if you notice wave packet width, I have sigma k and sigma x on the bottom. I don't actually have to directly adjust sigma x to make it bigger. I can make sigma k more narrow. And you notice that that second one responds. So I've made this more narrow, and now this is wider. If I want to increase the number of oscillations within one envelope, and this is assuming that I'm not actually changing what my envelope is. So I'm going to leave these alone, which means my envelope stays the same, and I'm just going to change my wave packet center. So that takes my average k value and moves it up. And so let me actually, it's a little bit tricky to see this, but if I try to count, I see like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So now I move it up. And okay, is it more? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 times 2 is 22. And obviously what's tricky is that there are small little oscillations out here, but this has given me more oscillations. If I go all the way down, we now see that it's certainly fewer. My envelope hasn't changed, and we've just changed my average K value. So the envelope is what we consider in many cases, but there's also the oscillations in between. Now we set K1 to be equal to 0. And now we want to say, okay, what is this going to impact in a physical particle's properties if we assume that this is modeling a physical particle? So if I increase K naught, right, I'm changing my K value, which corresponds to changing my momentum. These squiggles are in fact getting more close together, right? Your wavelength is decreasing of these little squiggles, but my envelope hasn't changed. But this would actually correspond to a higher average energy particle or a higher average momentum particle. That's how to think about this. So this doesn't have a very well-defined energy, which we'll come back to in the next part of the simulation. But if you were to make many, many measurements of momentum or many, many measurements of energy, as I increase K naught, the average value I would get is going to increase. If I decrease sigma K, and I have to first kind of make it big. So right now there's a certain wave packet width. And if I'm decreasing sigma K, that is increasing my wave packet width. So this means there's a greater uncertainty in position. So if I had an ensemble of identical particles, if I prepared a bunch of particles in the same way and measured their position, I would have a greater uncertainty in position as sigma x gets bigger, right? This particle is less likely to be measured in a tiny little narrow window, where this particle is very likely to be measured in that tiny little narrow window. But the flip side is I'm changing my uncertainty in K, which for a physical particle would correspond to increasing your uncertainty in momentum or uncertainty in energy. So specifically the answer is if we decrease sigma K, we now have decreased our uncertainty in momentum, we have decreased our uncertainty in energy, but we have increased our uncertainty in position. Now what if I switch my functions from sine to cosine? Now, there is the tiniest little shift that you see happen here, but nothing happens up here, and your envelope doesn't change. Sine versus cosine makes no difference here. So we wouldn't see anything change about the particle. And the key is going to be when we think about a real quantum mechanical particle, that in fact this is a complex function. So sine would represent, for instance, the real portion, and cosine would represent the imaginary portion. So sine versus cosine doesn't matter, and that was something I wanted you to think through. So in the next video, we'll go through the second part that actually looks at the quantum wave packet.